continuation of the first course on the glass transition and what is there to be explained about it. And I haven't finished with some pieces of the phenomenology that are probably important to explain. And okay. To do something about it. It was not fundamental what I said, so you didn't miss much. So again, what I was discussing was what is there to be explained about the glass transition. Oh yeah. The glass transition, and again seen from the supercooled liquid. So we saw the temperature dependence of the relaxation time and the viscosity, and important pieces of the phenomenology are also the time dependence of the relaxation functions. Okay, so you have something like we said, any observable that is used, being molecular orientation or related to the displacement of the particles, and you look at the correlation function time dependent, which is just a fluctuation of this guy, that is A of 0. And again, as you remember, we are in something which is in equilibrium despite the fact that it's metastable. So you have time, translation, invariance, fluctuation, dissipation, and all that, okay? Now, when you look at this function, it is, in simple cases, very simple cases, you would expect this function to decay as just a simple exponential with just one relaxation time. What you find in the supercooled liquid is that, in fact, the function relaxes, but with what is called a stretch exponential. And again, it's considered as significant. There are many experiments, fits using that. So that means that at long times, phi of t goes like exponential minus t over tau to some power beta, and beta is less than 1. Beta equals 1 is, of course, is a simple exponential, and beta is less than 1. In practice, beta is always more than 0.3, 0.4. Okay. So, and there is some evidence that this, so if you wish, if you plot phi as a function of the log of time, the exponential would be like this, and a stretch exponential will be slightly stretched. Okay, so this is why it has the name. Okay, and there is some evidence that the exponent beta somewhat decreases as you lower the temperature. So your system, okay, was, for the very simple one, was exponential at high temperature, and then you decrease the temperature, it's more and more stretched. Okay, so this is one thing, the non-exponential relaxation that is considered also as an important point of supercooled liquids. And the tau here, again, is the relaxation time that I have plotted several times, and it's the one that changes by decades, 16 orders of magnitude for some liquids. Now, what is also significant is that when you look at this function, actually, it's just not like this, is that when you lower the temperature, and again, this is, as a function of the log of the time, and this is, again, experimental data, and say that I normalize my function. Let me look at my graph so that it looks really like experimental data, okay? So at high temperature, okay, you have something like this. And when you lower the temperature, so the relaxation time, which is essentially this guy, will, of course, move, because it increases quite a bit. But what happens is that instead of having just the displacement of the curve, you have something which is like a two-step relaxation. That is, you have something that appears, okay, like this. So you lower the temperature again, you have something like this, and you lower again, you have something like this, and you keep going, okay, like this, for instance. So here in this direction, okay, you are lowering the temperature, and here this is the relaxation time that increases, again, on a log scale, so it can be 15 orders of magnitude. So you see what is significant. So the stretch exponential will be this part. Okay, so that will be the exponential minus t over tau to the beta. And then you have something here which is shorter time scale relaxation, microscopic relaxation. And you see that you have in between something which is like a plateau that, you know, increases in size. And this is a region which is called, more or less, the beta relaxation regime. So this is more or less microscopic. You know, again, it depends on the system. This is called the beta relaxation regime. And then this one, the final one, the relaxation time that we plot, is in fact called the alpha relaxation regime. Okay, so now you have several steps of relaxation, and they are separated by something like a plateau that increases in length as you decrease the temperature. Okay, and this plateau is, in real liquids, is fairly high. I mean, it's around 0.8, 0.9 of the initial value. Okay, so it's a fairly high value. And this is something that you can measure by light scattering techniques and essentially also by neutron scattering, and you can also, of course, measure by computer simulations. Okay, so what this is, I mean, this is actually a non-trivial behavior, because as I said, you could have slow dynamics and nonetheless no appearance of a plateau. You see that it's fairly constant in height, more or less. I mean, it increases a little bit, but it's fairly constant in height. And you could have a relaxation where, in fact, the whole thing shifts, but with no appearance of a plateau in two steps. For instance, this is more or less what happens in the case of the usual spin glass, so the Edwards-Anderson-Ising spin glass that we're already introduced, that doesn't have that feature with the plateau that appears and stays at a roughly constant value as the temperature decreases. So this is a non-trivial feature. It is just not the fact that you have a small microscopic time, a huge alpha relaxation time, and then in between you should have something, and then you say, okay, I should have a, you know, why not a plateau? Well, it's not that easy. Okay? Again, many models with slow relaxation, big difference of time, don't have a plateau. The explanation for this, okay, is, okay, let's take a very naive view and go back to the landscape picture. You would say, aha, but I understand what's going on, because, of course, here the guy is just short-time dynamics, and then it's stuck for a while. Okay? And it's stuck meaning that, okay, but it's stuck in a metastable state, in a, you know, in a basin of something, of a minimum, and it stayed there for a while until it can finally escape. Okay? So this is one piece that was actually used to let's say, to motivate at least the landscape picture, and one used, you know, in particular by Goldstein in the end of the 60s, is that this idea that you have a separation of time scales. So the liquid will spend time, you know, vibrating or having short time dynamics in a given minimum, and then, you know, at long times will escape from the minimum. And this, you know, again, in naive term, what was the idea that is that the particle is in a cage. So there was a big thing, this idea of a cage, that was considered as an explanation, but it's just a mere empirical description of what's going on, is that the particle, for a while, is in a cage and it just vibrates in a cage. So this is the real space picture, if you wish, the cage of what I said of being stuck in one minimum. Again, it's just a picture. It's not neither a theory nor a real explanation. What is interesting is that you will see, I guess, in a week, in a couple of weeks, is that this non-trivial type of time dependence is precisely what you find also in some mean field spin glass models, for instance. Okay, so the ones that were discussed by Giulio, the p-spin, you will see that it has this kind of behavior at the mean field level. And of course there, maybe someone will discuss it later, there's no notion of a cage, so you have to understand why the system does this plateau time of behavior before going to the alpha relaxation. Okay. And
so if there's no cage, what's going on?
Well, let me not discuss it now. Okay, you'll have all the, I hope you will have all the several courses on the dynamics maybe of the p-spin at what is called the mode coupling theory. Okay, which is what describes at the mean field level, let's say, this type of behavior.
But do you also think that there is no cage in actual physical structural glass?
No. In a physical glass, when you see simulations and everything, you see that the particle is indeed caged by the neighbors. The reason why it's not an explanation is that you have to explain why the neighbors don't move and are also caged. So you have something that has to say, why is the cage a relevant concept? Because the particles then do not move, in many places of the system, and the cage are just blocked in a sense of, again, not contact, by the other cages in the system. And when you do the p-spin model, of course you have a spin, it's hard to believe that you have a cage in the same, with the same meaning as the cage in the case of a liquid. Yeah?
So does the Stretch exponential imply more than one relaxation factor?
Okay, I was maybe about to discuss this, but let's do this. Formally, you can always write this, okay, as being, of course, can you still read down? Okay. You can formally do this as an integral, okay, over some relaxation time. Okay, so that, of course, and you can find the, I don't remember what's the probability of the time, but it's easy to derive. Okay, you can always write this as this, saying that it has a distribution of relaxation times. Yes. Now, this is just a mathematical rewriting of the stuff. It doesn't mean that you have actually in the system different regions with different relaxation times. Okay, and that's been actually, I will discuss it a little later, but it's been one of the starting points of a discussion of, but indeed, can we prove this? That indeed you have regions which are slow, regions which are fast in the liquid, and you have indeed something which looks like a distribution of relaxation times. Okay, and that's what I will discuss later, which is, in fact, the observation and then the proof that the dynamics actually are heterogeneous in the system. So it's not like everybody reacts the same, is as fast everywhere in the system, is that indeed you have slow regions and fast regions, again, over a certain time scales. But that's true. That was something that puzzled people, and they tried to explain it that way in terms of distribution of time scales. Okay, so this is for the relaxation, and now what I'd like to move to the static quantities. Yes.
This is all still supercooled, right?
Yes.
We're getting closer to not crossing.
Exactly. Everything is supercooled. That is, the system always relaxes. Okay. And well, let me not enter in the mode coupling theory and what would happen in the, if you were in a glass, what would happen is that at some point, basically, you see in your experiment, at some point your plateau here, say you have an experimental time which is around here, and your plateau keeps here, and you do not see any decay of the plateau. Okay, so your system is stuck now in one of those minima, and no longer relaxes on the time scale of the experiment, and then that will be a glass. Okay, but here, so long as you have relaxation on a given time scale, this is still the supercooled liquid. Yeah.
The time scale is logarithmic here, right? So it's not just that it's 5 minutes longer,
No, no, it's logarithmic. So it's still the same idea that the relaxation time increases by those 16 orders of magnitude. So you have to work on a logarithmic time scale to see this. Okay. All right. So on the static part, what happens is that at the same time, so the dynamics again was pretty, dramatic or interesting. And then at the static level, you see that there is very little changes in the statics. Okay, and let's say in the observed, that will be better, statics, because we will. Of course, the idea is that maybe there's something deeper than is not easily observed. And the first thing is that there are very small changes, for instance, in the structure measured, so the static structure measured by pair correlation functions. So for instance, by the structure factor, the S of Q, which is just the correlation function of the density fluctuations. Okay? So this is a density fluctuation. So delta rho of Q is the density fluctuation at the wave vector Q. Okay? And this is a fluctuation. Okay? And this is just a correlation function of this guy. So this is what we measure, what people measure in neutron scattering or in X-ray scattering. And this is the Fourier transform of the pair correlation function, in space. That is also something that measures what's the probability to find another particle at a given distance of one particle. Okay, so this is just some kind of average pair structure that you measure that way. And this structure factor, for at least for atomic liquids, looks something like this. This is, roughly speaking, 2 pi over the distance between particles. Okay, so this is the main peak. And then it has a structure like this. Now, when you cool the system and you go, say, from melting down to the glass and even in the glass, well, you'll see that this guy will change maybe like this. Okay. It's barely observable. It's a little change, but it's very small. And if you try, so this will be, for instance, the liquid even above melting or at melting, and this will be the glass. Okay, so the green is the glass, and the white is the liquid at melting. So you see the change is very little. And if you try to extract, as usual, a correlation length from this, psi, let's say 2 to say that it's related to pair density correlations, well, it changes by 2-3%, a few percent change. So it is very small from melting to TG and below TG. Can you measure what? Yeah, well, you do a neutron scattering or diffraction experiment. You do it at a given temperature. Okay, so when you're at melting, you have the liquid, and then what you do is that you cool the liquid, and you can do it pretty slowly for many. Okay, atomic liquids, it's as I said, it's something that actually doesn't really form glasses except metallic glasses. In reality, what people look at in experiments is molecular glasses. For molecular glasses, since you have many atoms in the molecules, the structure of this function is a little more complicated, but it's the same idea. But anyhow, you cool the system in your sample, and then you measure again the neutron scattering data, and you measure it also in the glass. So you can do it reversibly, at least down to TG. Then it's, of course, you have irreversible processes. And it's what you observed. Okay? But it's a fairly routine experiment. Now remember, if you had a crystal, then the crystal, of course, will be something like this, right? That is, the crystal would have Bragg peaks and would have, because of the periodic arrangement. So this is also what tells you that the glass, is disordered because it doesn't look anything like a crystal, even a broadened crystal. Okay? So this is what tells us that first, the glass structure is disordered. This is one of the motivations for telling this. In systems where you cannot just image the sample, and also it tells you that it doesn't change much. Okay, which is of course very different from the liquid gas critical point, where you would find a huge change, of course, of the pair density correlations as you approach the critical point. Now, there is one quantity that varies more in a significant way. So let's say the only significant variation relates to the entropy. Again, of the supercooled liquid. And in fact, more than the entropy, what is more interesting to look at is, what will be called, or what has been called, the configurational entropy, for a reason that I will discuss later. But in practice, what has been measured is the entropy of the liquid minus the entropy of the crystal. Remember the curve that we had. Okay, so you have below melting. Of course, this is only below melting, because otherwise there's no crystal if you're above melting. But below melting, you have a curve which is the liquid curve, and you have another curve which is the crystal curve. And you can take the difference between those two. And this is something that was done by Kauzmann. There's one N or two N's, you never know. In 1948. And so you have this sort of a plot. So let me call this delta S for now. So he plotted delta S divided by delta S at melting as a function of T divided by T melting. Okay, so this is 1, 0, this is 1. And again, let me try to see my notes, so I try to reproduce. Well, I guess there are two N's. I never remember if Kauzmann has 1 or 2 N's, but I think it has 2 N's. And what you see is that for some liquids, okay, so you would expect this maybe to go to 0 at 0 temperature, but for some liquids, you find a behavior which is pretty striking, which is something like this. Okay. So the entropy, the difference of entropy, decreases, and here you are at Tg. Okay. And of course, at Tg, as we already saw, this guy goes on a different slope, because now it is a glass. Okay, so the glass is out of equilibrium. This is not what is of interest here. What is of interest is the branch here, which is the supercooled liquid. And what is fairly significant is that you have, let's say, a decrease by a factor 2 to 3, and over something which is, again, a small change, the 30% of change of the temperature. Okay, so the entropy, or the difference of entropy, decreases by a factor 3. This is something to be taken seriously. Okay, it's not something which occurs everywhere all the time. So this is the significant observation that was made. Now you have other systems, for instance, say this will be again our orthoterphenyl Okay, and it decays something like this until it's Tg, and then maybe this one decays by a factor of 2, but let's say many systems it decays by a factor of 2 to 3 for molecular liquids. Remember the strong glass formers that I discussed, the one, for instance, made by silica, which have an Arrhenius behavior. Well, those guys, they decay by much less, and then they become a glass. Okay, so this really seems to be significant for the fragile systems, which are, of course, those are the most numerous, and something that then correlates, if you want to do this, with the super Arrhenius slowdown of the relaxation. Okay, so this is empirical observation. Okay, there's no, so far here, there's no theory of anything. Now, just a few comments on this. The first one is that what's the rationale for subtracting the crystal entropy from the liquid entropy? Well, again, what Kauzmann had in mind is that you wanted to separate a kind of trivial contribution to the entropy, which is that due to vibrations. Okay, you vibrate around minima, for instance, and that, of course, gives rise to an entropy. Now, these vibrations, okay, the glass is a solid, the crystal is a solid. Of course, they are different, we know, but, in a minimum, let's make the assumption that the vibrations are about the same. Okay. You vibrate around a minimum, okay, you get the same entropy. So this is the approximation. Okay, it's the approximation that basically the entropy of the crystal gives you an idea or an estimate for what would be the contribution of the vibrations to the entropy of the liquid. Okay, well, it's been studied. You compare the entropy of the glass to that of the crystal. You see if they are very different or not. It's not a stupid measure. Maybe it's not very accurate, but it's not a stupid measure. So as a result, the difference between the liquid and the crystal entropy is something which is, again, the configurational entropy, an estimate of the number of available states. Because once you have removed vibrations in each state, you have a measure of the number of available states. Okay, so this is, of course, it's an entropy, as Giulio mentioned. So the entropy will be the log of the number of available states. Remember, the number of available states in that case would be exponentially large in the system size, and the coefficient of is given then by the entropy. Okay, so right, so this is telling you that yes.
So this entropy is at the same temperature. This shouldn't have the same temperature.
Yes, of course. It's the entropy of the liquid at temperature T minus that of the crystal at temperature T. It is supercooled liquid. So you can do this only below the melting temperature. Okay, above, you would have to do extrapolations, and so people have played the game. But let's say Kauzmann did it below the melting temperature. Yes. But there's nothing fundamental about the melting temperature. It's just that it's, in practice, it's up to that point that you can measure the properties of the crystal. Above it, there's no crystal. So it's very hard to superheat the crystal. Okay, so again, the idea is that, well, the number of available states to the systems then decreases quite significantly, because again, this is a log scale since the number is the exponential of, significantly between the liquid at melting temperature and the liquid when it approaches the glass. Okay, so this is one major observation. And what he also said is that, well, okay, here what I do, of course, is remember, it's time scale dependent. That is, it depends on the rate at which I cool the system. So if I cool it a little slower, I go down a little bit. He said, well, okay, let's extrapolate and imagine I could cool infinitely slow the system. Well, you extrapolate, by reasonable functions. And you say, oh, okay, well, if I extrapolate and there's no change of curvature, which also could always happen, you will reach here a point, let's call it Tk. You will reach a point where the entropy of the crystal is equal to the entropy of the liquid. Well, it's not forbidden, of course, but it's weird, right? You have the entropy of an ordered, fully ordered space, phase, which is the same as the entropy of a fully disordered phase. And then, of course, if you keep going, the difference of entropy would be negative, which would be even weirder. Okay, so this is what was, called the Kauzmann paradox. And something which looks like an entropy crisis. Entropy crisis meaning that the configurational or delta S is equal to 0 if T is equal to Tk. Again, for liquids, this is only in extrapolations. Okay? When the glass that you form, when you can go, the entropy is still quite sizable. Okay, so it's still something which is, of 1/3 of what it was at melting, meaning that you have still a lot of available states, except that you get stuck in one, but you have many available states. But if you could extrapolate, then, well, you would have that entropy crisis. And the reason why I, of course, mention this, stress this, is that this is, again, one point that can make the connection, that helped made the connections and actually suggested at first to Peter Walliness and his co-workers the idea of looking at rough landscapes. Is that what you need is that you need something to describe this. If you really believe that in some ideal world you will go to a temperature where the entropy vanishes and that this is basically a description of the available number of states, well, you need a model or a description where you have a rough landscape where you have an exponentially large number of states. The exponentially large number of states decreases as you lower the temperature of available states, decreases as you lower the temperature, and at some point, despite the fact that you are disordered, you reach a point where the entropy becomes sub-extensive so that the number of states is no longer exponential. Okay, and this is the connection, of course, that kind of rough landscape is precisely, again, it's not easy to find a model that has this kind of behavior. And this is exactly, of course, what you find in the mean field descriptions that were discussed by Giulio. Okay, for instance, for the random energy model and for the p-spin model. So at first, that was this idea and the connection between the two, is that you realize that, in fact, those models are some kind of idealized realization of what is observed here. Now, it doesn't mean that it's the right description. It doesn't mean that this guy goes indeed to a TK. But nonetheless, it's a way to rationalize what's going on here. And again, there's more to be said and more will be said about the mean field description that goes beyond just those simple models. But this is one point of connection with yes.
But is it obvious how to map a real particle system on a triplets of spin, like in the p-spin model?
Oh, what a good question. No, again, what I'm saying, and I think it's you want me to answer this question that will be asked over and over again. Here we are just functioning by analogies. Okay, it's not that. I mean, in the original papers by Walliness and Kirkpatrick Thermoli on this issue, it's not that you're trying to mimic the liquid. Okay, you're not trying to say, hey, my liquid looks like this, and if I take that particle plus that one, I can think that it looks like a spin, and then this spin has triplet interactions, but with random couplings. It's not the way it was done. The way it's done is different, is that you think of a description in terms of the landscape, energy landscape or free energy landscape, and then you say, what are the models that can give me that landscape? Okay, so it's a different, Everything goes, I do not map the p spin to the liquid. I look at my liquid, I imagine has this kind of complex landscape, and then I'm looking for a model that has the same kind of landscape. Okay, so it's an indirect description through the landscape. And the REM and the p-spin are models that gives you a landscape that can describe, roughly speaking, this behavior. And again, as I said, the landscape picture comes from also this idea that indeed there is a separation of time scales with particles vibrate and then are stuck in minima. And of course, you keep out, in a spin, there's no vibration. So you take out vibrations, and you just have to count the number of minima or free energy minima if you're in mean field. So now this is one important point, is that the connection is not a direct connection by mapping the liquid to the random energy model. What we know, on the other hand, is that there are, and again that was mentioned by Giulio, you can take mean field models now of particles and liquids. So you take a liquid, a hard sphere liquid in infinite dimensions, and then you see again that then the infinite dimension liquid is a real particle system. Okay, it's infinite dimension, so it's weird, but okay, it's still a liquid. And then in that case, you can realize that the landscape again is the same as what you were expecting here, and it's the same as what you computed in great detail for those guys. But again, it's a universality via the landscape, okay? Not a direct mapping between variables. Okay.
In this mean field, in the mean field description, can one also see this entropy crisis? Or?
Yes, precisely. That's what Giulio did yesterday, is that the mean field description has the entropy crisis, okay? The liquid, not really, because you don't know, but those models have exactly the entropy crisis at the given temperature Tk. Okay, so yes, precisely, these are models with an entropy crisis.
Is Kaufman Tk related to the finite temperature divergence of the reactive form?
It's a good point. It's a good question. Again, we were in the liquid. We were talking about empirical observations. Okay, so empirical observations is that indeed when you fit the relaxation time as exponential a over t minus t0. Okay, you do a fit. Then you extract the t0. And then you say, okay, I fit the configurational entropy, I have a Tk. Well, it turns out that T0 is not very far from Tk by empirical extrapolations. Again, you're making extrapolations here and there, so it's not saying that they are equal. There's no way to say that they are equal. But let's say that it's not unreasonable to say that the two temperatures obtained by extrapolations are, reasonably close. And again, as I said, you can rationalize the fact that the decay here is related. Again, it's a correlation. A lot of correlations in the business of the glass transition. Empirical correlations. But you see that the increase of the activation energy, well, correlates somehow with the decrease of the configurational entropy. Okay, so all these are observations, correlations. Again, it's not a theory, but it's what is observed and gives insights to develop theories. Yes?
Is there any sense in which something discontinuous might happen at T2? Is there any notion that something discontinuous might happen?
Well, first, well, there's okay, but in observations, okay, the discontinuity, I mean, here it's just a divergence, and here it's something going to 0. Now, of course, you could say, okay, but what if I plot then tau as exponential a over t times delta s? Okay, so there's no, I'm sorry. So there is no discontinuity, there's one thing going to 0 and one thing diverging. Okay? Well, this is a very significant singularity. Okay? This is something which would look like an ideal glass transition, where your relaxation time is truly infinite, so your system is a real ideal glass, and your configurational entropy now is strictly 0. I mean, the extensive configurational entropy is strictly 0. Well, let's say this is not right, and then I have to divide by the number of particles, because otherwise it would be too big. So it goes to 0. So yes, and this is indeed something that was suggested. I will not have time, unfortunately, to describe this to you, but in a phenomenological theory, that is the Adam-Gibbs theory in 1965. Okay, so that was one attempt to say, hey guys, but this decrease of the configurational entropy correlates with the increase of the relaxation time. Let's try to cook up a mechanism that would indeed relate the two. And they came up with a mechanism, some phenomenological approach, where the log goes like 1 over then the configurational entropy. Okay? So this is something, again, that will be used by theories of the glass transition. And again, remember mean field, well, remember, I will discuss this later. Mean field tells us something about the configurational entropy. It doesn't tell us beans about the relaxation time and the activation, okay? Because it's not contained in mean field. But the scenario with the entropy crisis and the behavior of configurational entropy is nonetheless contained. Okay, so I guess this...
Sorry, one more question. So yesterday in Julio's class, he mentioned the threshold temperature, and what's the corresponding temperature? Or threshold energy. So is that energy scale corresponding to which temperature?
Okay, let me do a slightly different plot then. Just that you can make the connection with the threshold temperature or energy and all that. This is in a mean field description, and it goes to what I said here to the mode coupling theory. Okay, so I'm going back to the 1 over T log tau behavior, okay, with something that was, let's say, about Arrhenius and then strongly super Arrhenius. Now, this was Tg. Tk is, say, here. Okay, Tk or T0, but let's assume that they are the same for now in the models. Then what happens is that when you describe the system in mean field, you have what is called a dynamical transition, at which the plateau goes to infinity, and this takes place empirically at a temperature, let's say, dynamical, which is around here. Okay, so basically what this would say, now this is done by fits, again, all this is done by fits. Okay, so this is the mode coupling theory on which you will have courses in the following weeks, so I'm not going to say anything about it, except that it's also contained in the mean field description, that one. And basically this is when you reach, modulo energy versus temperature, but this is when you reach threshold. Okay, so threshold is here, the entropy crisis is here. So where you have a non-trivial energy landscape dominated by minima, as in the calculation done by Giulio, is basically between those two temperatures. Okay, so this is the rationale, at least, of applying the mean field description of those models to liquids. Okay, so now what I wanted to do is a couple of, again, comments, digressions about the slowing down of relaxation. What is unique about the glass formation. Now, what we saw is that, we discussed this already, so I will be short on this, is that there is a non-collective or non-cooperative description of slow dynamics, which is the Arrhenius form. And this, we said, takes place, you remember, well, you have, for instance, a chemical reaction. So you have reactants, you have products, reactants, products, and you want to know the time scale to go to from here to there, from there to here. Okay, it doesn't have to be exactly at the same level. And you have an energy barrier. Okay, and here I had the questions the other time. So this is now an energy barrier. At the beginning, not a free energy barrier, because this is something which is due to internal degrees of freedom, and this is really an energy. And of course, when you are at temperature such that delta U is much larger than the temperature, it's where you use many ways to derive it, many different approaches. So this is when you use the Arrhenius law, when you say that the time to go from here to there and there to here is some attempt time times exponential delta U over T. Remember, KB is 1 in this description. Okay, and here it's non-cooperative because basically you have few paths from going from one reactant to the products, so there's very little entropy, and say the solvent around, so all degrees of freedom, well, sure, they do some modification to the energy, but it's subleading, okay, subdominant. So this is a strong Arrhenius law with an energy that is essentially constant as you decrease the temperature. And again, it's because the number of degrees of freedom truly involved in the event doesn't change with temperature. Okay, so nothing collective in this behavior. Of course, you need fluctuations from the bath, right? So you need still the environment, but there's nothing collective at the level of forming the barrier. The barrier is there, and it doesn't change much. Now, a quite different, the paradigm, I would say, for a collective slowing down is, of course, the critical slowing down. Here, it just take a simple critical point, conventional one, okay? For instance, the liquid gas critical point, or the Curie-Weiss paramagnetic to ferromagnetic transition. So it's conventional. So you have a critical point at Tc, which is different than 0. And what you observe is that, of course, when you approach Tc, say from the disordered phase, from going from high temperature phase, as T approaches Tc, you have a correlation length, of course, that diverges, like, say, T minus Tc to some exponent, nu. Okay, so that's the usual thing. But you see also that the relaxation time actually increases when you approach the transition, the phase transition. But it increases as a power law of the correlation length. Okay, and Z is called the dynamical exponent. And it's of, let's say, of order 1 for usual dynamics. For instance, for non-conserved dynamics, for the Ising model with heat bath, Glauber dynamics is just about 2. Okay, so this is the usual critical slowing down. Now you see what it does is then when you combine those two, often that means that tau increases like T minus Tc to the minus Z nu, where again, this is a number from, say, 1 to 4, something like this. So the relaxation time diverges, but it diverges as a power law of the temperature. So this is quite different. Again, neither this one, which is non-cooperative, nor this one describe what we are looking for, which is something where the activation energy increases, so it's clearly non-Arrhenius, it's super-Arrhenius, but it increases not as a power law, it increases maybe as something like, you know, at least in one of the formulas, for instance, diverges, but it's in the exponential, okay, not as a power law. The power law is in the exponent. It's not just like in the conventional critical point. Okay, so this is again telling us that the slowing down that we observed is nothing comparable to what we know from simple models. Now, there are, let me see, there are a couple of models where it's different, and this is what I will discuss now. There are, and again, it's analogies. I'm not saying that this is the explanation. I'm just trying to see, if I look at, you know, the ocean of models that have been studied, are there some of them that looks like what we observed in the slowing down of supercooled liquids? Now, one is what is called the activated dynamic scaling, in which something which is, you know, closer to what we're looking for. Because in that case, what you have is that the relaxation time increases as an exponential of the correlation length divided by the temperature. Okay, so you see this, if you are at a critical point where this goes like T minus Tc to the minus nu, so it's a conventional critical point from the standpoint of the correlation length. It's still a power law, but again, the relation between length scale and time scale is exponential. And of course, this is what we would like, because this is closer to the description of, you know, in terms of the Vogel-Fulcher law here, where the divergence here is in the exponent is not as a power law. Okay, well, here the power law would, here the exponent will be is 1, but okay. And this type of behavior does exist in rare models, I would say, which are disordered models, that is, models with quench disorder. In which the critical point is controlled. I'm going to throw you the words at you and then give a few explanations, but not go into the details because you might have more on that in the last weeks, is controlled by a zero temperature fixed point. And of course, this is a renormalization group term. Okay. All right, so I will explain a little bit what it means, but the few models that we know like this are the random field Ising model that was discussed a bit by Chris Moore yesterday, and the, let's say, random elastic manifolds. So you have an interface in the disordered medium, and you're looking at how the interface moves under thermal motion. Okay, and I guess this is something that will be discussed by Pierre Ledoussal in the following weeks. So those.
About the relaxation time formula, is the exponent for the correlation length or just a function of
Psi.
Okay.
It's a psi. No, I'm sorry, it's not 4. No, that would be, no, sorry. It's a psi. It's an unknown exponent, okay? Well, it's unknown except for some models, okay? Now, just in very rapidly, what does it mean just to for those systems is that you have, for instance, the random theorizing model has a critical point, a usual critical point from paramagnetic to ferromagnetic in dimension larger than 2. And there is now a phase diagram, if you want, which is temperature, and delta is the strength of the disorder. Okay, so you have random fields, and which are, that's the variance of the random fields. Okay, so this is the disorder. Down here is, of course, just a theorizing model, and you know that you have a TC in 0 disorder. And what happens is that you see that there is a line of critical points where here you are paramagnetic, here you are ferromagnetic, and here you have a line of TC. Okay, so at constant disorder, for instance, you decrease the temperature, and you have a critical point, and then you enter a ferromagnetic phase. Now, remember, and that's the reason why I spend a little time of this, is that this guy will have fancy dynamic activated scaling, but from the point of view of the ground state and the low temperature properties, Chris Moore told us yesterday that it is not glassy. Because this system, just by the mean max flow, you can find the ground state in polynomial time, okay, despite the disorder. Okay, so this guy is not in the class of rough landscapes that were described by the REM, the p-spin, and all that. It's something for which you can find the ground state in polynomial time. Okay, nonetheless, what happens is that when you study the critical point now, okay, you do renormalization group. Not easy, but let's say you'll have more on that. Renormalization, as you know, is about you coarse grain your system, you include fluctuations over a given length, and then you rescale so that you can compare it to the original system. Okay, this is all I want to say about renormalization group. This is short, I know. What happens is that when you look now at the renormalized quantities, so you can fold a number of quantities by doing these procedures, and at the length scale L, at which you have now coarse-grained, you can define renormalized quantities. So for instance, you can define a renormalized temperature. And what happens is that you follow this temperature. Well, this temperature goes to 0 as L goes to infinity. L goes to infinity means that you have included all the fluctuations in your computation. And you are at the fixed point. Okay, so this is the fixed point. Now you see what means a 0 temperature fixed point means that the exponent theta is larger than 0, so that the temperature, renormalized temperature, goes to 0. So we like to draw, flow curves like this. So everywhere here, okay, you go to this fixed point here. This fixed point is critical, so it's unstable, blah, blah. You can do all flows. So this is the meaning of a 0 temperature fixed point. And it's basically somehow necessary to have a 0 temperature fixed point to have activated scaling. And the reason is that, of course, when you start your system from here, from renormalization, what you know is that it will follow this curve for a while and then, of course, escape. But then, as you renormalize, it will go, in fact, to low temperature. That is, even if you started from high temperature, it will go to low temperature. And at low temperature, if the system itself, the renormalized system, is at low temperature, well, then you can use the Arrhenius formula to describe the relaxation time. So basically, you will have a relaxation time on length L, which goes like exponential some energy U divided by the renormalized temperature, which goes to 0. Okay? And of course, if you put this together, this guy goes like this. Well, okay, that says that if U itself does not depend on the scale, which is the simplest assumption, then this goes like U L to the theta divided by T. In that case, what that means is basically, well, you can do this for L, of course, of the order of the correlation length, which is the place where you want to, and that tells you that psi is equal to theta. Okay? And in fact, it's something that, in that case, you can show by using the functional RG techniques. Okay? So it's something that we did, and something that will be explained for the other model by Pierre Ledoussal. Anyhow, this is a model then that is not like rough landscape, but has a zero temperature fixed point, so non-trivial excitations, and then something which is activated. But you see, it's not a model for a glass. So we cannot just transpose this. But if you want to put a critical point, you need something with properties like this. Well, it's not glassy in the sense that the idea about a glassy landscape is that you have a lot of competing low energy states, so that it will be very hard to find the ground state of the system in a polynomial time.
But in the physical system, it follows some realistic short scale dynamic, short range dynamics. So here it is taking exponential time to relax the region of size.
Yeah, but it's not related to the complexity of the landscape. It's related to the fact that you have rare excitations in the systems, droplets that are rare, that are large on all scales, and it diverges because you are at the critical point. So yes, it is a complex dynamics. Okay, it is a very slow activated dynamics, but it's not what is considered as what would be a good description of glassy dynamics, nor comparable to the analogy between the optimization problem, the hard or all the hard problems in computer science and glassy phenomenology. Okay, so this is simpler for that point of view, but this is.
In real glass, physical glass, as opposed to infinite range model, how do you know what rather that they're really?
I don't know.
Closer to the infinite range model versus
I don't know.
more realistic model?
I don't know. What I know is that just by looking at the random field Ising model, I cannot just explain the Kaufman plot. Okay, for instance. But okay, otherwise, the problem is still open. So now here I'm stressing the dynamics, and I'm overlooking the entropy and the structural problems. Here there's okay. Let me keep going and go, because that's something I would like to discuss to finish this course, is, yes, is the problem of, and I said I will come back to that, so it's the problem of nucleation and metastability. And again, we're still discussing in a way activated scaling. Okay, it's a different way to obtain activated scaling, and it's a way that also formally can be related to a zero temperature fixed point, although it's not the way it's done usually. So let's say at the Landau level, so mean field, so discussing mean field. So you see van der Waals theory of liquid-gas transition, Curie-Weiss theory of ferromagnetism, or general Landau description. And metastability means that for some range of parameter, okay, so parameters being the external field, the temperature, the chemical potential, whatever. My free energy for some order parameter. So this is a Landau description. So this is a uniform order parameter, density if it's liquid gas, magnetization if it's Curie Weiss, and here it's the free energy. But in fact, when you plot the Landau free energy, it's the free energy, remember, per volume, per unit or per number of degrees or freedom or per volume, okay, N or V. So this is a free energy density that actually always plotted. Okay, and then you have a metastable state, and you have a stable state, and let's say, okay, we have a difference of free energy here, so this one is less stable than this one. This is why it's metastable. And we have a barrier here. Oh, that's not well. Okay, let's call it delta F dagger, something like this. Okay, so this is Landau description. Now, if we do a kind of naive, and of course, first order transition, is when you change the control parameters, and at some point you can shift this second minimum so that it becomes at the same height as the stable one, and then you have coexistence of phases, and you can have a first order phase transition with a discontinuous order parameter. Okay, so you have a discontinuous order parameter, and it's a first order transition. Now, in that case, if you do a naive estimate of the time to escape from the metastable state, well, it would say, okay, if the barrier is large enough, I will use tau as being just given by an Arrhenius formula. Okay? So exponential of 1 over t times the barrier. So the barrier, of course, is delta F dagger. But remember, this is the free energy density. This is not the free energy. So it's delta F dagger times V the volume, or N the number of particles. Okay, so if you do this naive estimate, and you're in the thermodynamic limit, well, of course, this goes to infinity. Okay, so your barrier is infinite. So when you use just mean field description with just a simple homogeneous mean field Landau potential, you of course end up with the result that metastability can be there forever. So there's an infinite lifetime of the metastable state. Okay, so this is why when you discuss mean field models, actually, the barriers between states are infinite in the thermodynamic limit, so you can really discuss free energy landscape with states that have an infinite lifetime. So it is meaningful in mean field to discuss a free energy landscape. Of course, the problem now is that this one? Yeah. Well, it's just, well, of course, you could have, to be non-zero. You mean you want to talk about the spinodal? Well, of course, this barrier, you could, if you change the parameters, as I said, you can reach, one state where the two guys are equal, and this is, as I said, the first order transition, coexistence. Now you can reach, if you go the other way around, you can reach a place where the second minimum disappears. And this is called the spinodal. Okay? And there, in principle, of course, you no longer have a barrier between the metastable state and the stable state, because the metastable state becomes unstable anyhow. So it has a flat direction to which it can escape to the stable state. Okay, so this is a spinodal, and it has some connection, again, with the mode coupling theory, with the threshold states, and everything. Okay, so this will be a description, if you wish, you will learn about this, about TK being something like this, and the dynamical transition being something like this. Okay, but here I'm in a region where I have truly the metastable state. What happens is that, of course, in a finite dimensional system, in finite range, finite D, well, this is not what will happen, because this, again, is only when I consider homogeneous solutions or order parameter. But my order parameter fluctuates in space. Okay, it's not a phi, it's a phi of x. And then that means that I can find states which are localized in space, okay, with phi of x, if you wish. And I can find barrier states, which are just localized in space, which are localized excitations, if you wish. Now you're allowing for something which is inhomogeneous. And you're asking yourself, well, are there solutions that are less costly than just having to move everybody a little bit and cross this extensive free energy barrier? And now I can do it because I'm no longer in mean field. I'm in a real three-dimensional system. I can do it and have localized solutions. And again, this is something which is, in that case, which is, you know, either the classical nucleation theory, okay, or you can do by just field theory and what are called the instanton calculations. And it's been done, for instance, by Jem Langer, I don't know, in 68, something like this, in the late 60s. And it's been also done by Coleman in quantum field theory. So this is this idea that, again, you're looking for inhomogeneous solutions where the excitations is localized. You don't need to move the whole system to relax the system. And the calculation of classical nucleation theory is that you consider what happens when I have a droplet. I am in my metastable state, okay, and I consider what happens if I have a droplet of the stable state in my metastable state. Okay, so I'm in my metastable state, and then I say, okay, but let's put a droplet of the stable state of size, say, R, something like this, okay, in the metastable state. And this has, because I'm at finite temperature, it has a finite probability, which will be the Boltzmann probability with the free energy difference between this excitation and the stable, the metastable state. And well, what you see is that there is a gain of doing this, of course. So the free energy difference between this situation and the situation without a droplet, well, you have a gain, which is just what you gain by having the stable state. So the delta F you gain, okay, times the volume of the droplet, because again, that was a free energy density. I forget the prefactors and the numbers in front. But then there's a cost. And the cost, of course, is to accommodate two different phases. And this is an interfacial tension. So this is a cost that goes, of course, like the area here. So this is the surface tension times some R to the d minus 1. Again, plus prefactors. Okay. So this is something like, look like this. Okay, something like this. Delta F. And the idea, of course, is that what you have to do is the barrier now, the maximum barrier you will encounter is the one here at the maximum with a critical value RC, which is just the one that minimizes this guy. Okay, it's the maximizes this guy. Okay, easy to see. You either do the derivation or you just compare terms, that RC is of the order of sigma over delta F. Okay, just by maximization of this. Once you have a droplet that is larger than RC, the system will want to keep being in a stable phase, okay, because then everything rolls down to the stable phase. This is just simple nucleation. Now, by Boltzmann probability, that will tell you that the time for nucleation okay, there are some subtleties that I want to discuss. But the time to nucleation is not exponential in this free energy barrier divided by temperature. But this is finite now, okay? Because the droplet is a finite quantity. It has a finite radius, except when it diverges. And then this free energy is finite. So this time is no longer infinite. It is now a finite time scale for nucleation. And you see that delta FC you can rewrite as, since the two terms have the same order, something like a number times sigma times RC to the d minus 1. Okay, times a number, of course, in front of it. Okay, so this is essentially exponential a number times sigma RC to the d minus 1 over t. And you see that it looks like, again, activated scaling, you see, here with a scaling exponent psi, which is d minus 1. So you can think of this behavior as being also related to a zero temperature fixed point, which is actually related to the discontinuity for fixed point of the first order transition, and with an exponent which is just the trivial exponent of the interface. This is just nucleation, okay? And RC, again, is given by this formula here, meaning that when you are at coexistence and delta F is equal to 0, that was Leo's questions in the first course, of course, RC is infinite, and then the nucleation time is infinite. So when you are at melting, for instance, it needs an infinite time to go from the liquid to the crystal. Now what happens is that when you lower the temperature, for instance, you will have a different behavior, and now I will show the curve, a curve which is measured. So this is for crystallization from the supercooled liquid. Okay, what people measure empirically are what are called TTT curve, time temperature transformation curves, where you plot the, well, let me plot it again, the log of the time versus the temperature. Okay, so here at melting, okay, it diverges, then it goes down, then it goes up. So you see that there is a minimum time for crystallization, which is the dangerous place, where when you supercool your system, you want to make sure that your cooling rate is fast enough that you can beat crystallization. Now, here it's dominated by nucleation. Okay, on this side, actually, it's nucleation plus growth. That is, of course, you have nucleation, but once you form your nucleus must grow, of course, to have the full stable phase. And it grows with something which is related to intrinsic dynamics of your system. And if you're in the supercooled liquid and your dynamics is damn slow, well, your growth rate is damn slow. So this is a reason why, not only the nucleation rate, of course, diverges as T temperature 0, but also the growth is extremely long. Okay, so this is why if you can beat, again, that dangerous spot here by cooling a little bit faster, and again, it depends on the liquid, well, then you can keep supercooling your liquid and you're safe for a while. Again, it has a lot of subtle details that I'm completely overlooking here. They are nicely discussed in the review by Andrea Cavagna, which is called Supercooled Liquids for Pedestrians. And, well, I have somewhere the archive number. It's in Physics Reports, but let me give you the archive number. 0903 4264. No, the low temperature behavior here will include growth. Okay? No, it is also the prefactor. There is a prefactor here, which is you will need a growth time. And this time again, since this liquid is becoming slower and slower on a time scale that is, super Arrhenius with temperature, will also grow extremely rapidly. So everything on this side will grow extremely rapidly. Again, the subtleties are what mechanism we're looking at, and that, but I have no time to discuss this in detail. Okay, so this is one first thing that goes back to crystallization. So, and again, it's a question, as I said, of time scale. Now, what it is also telling us is that, as I said, in principle, metastable states cannot stay forever. Now, if the time scale is the age of the universe, we don't give a damn. But if the time scale is smaller, for instance, in a supercooled liquid, you know that the system relaxes from, not to the crystal, again, but relaxes from maybe one of the available states of the landscape description to another of the available states of the landscape description. So the crystal is out of the way because we assume that the time scale is much longer. But nonetheless now, you're really relaxing. So that means that if you relax, well, then your metastable state no longer exists. And of course, there's nothing now like a free energy landscape because you know that your free energy should be convex. Okay? So when you are in a three-dimensional liquid, it's very hard to define a relevant landscape. The mean field is free energy. What you could do is define the landscape through the energy, and maybe Ludovic will discuss this. So the energy is well defined. It's always well defined. It's a function of the coordinates. You can define minima and all. But it's not clear that the minima are relevant. They can be separated by barriers that anyhow are very small, of the order of kT, so the system will never be localized or vibrate in those minima. So you need, you can do things. It's not that it's impossible, but you see that you have to put something like a threshold of time. You have to find a time-dependent landscape. You have to find tricky ways to try to apply the landscape picture to a finite dimensional system where you can always escape from a metastable state if the time scale is enough. Because remember, in crystal, what you have is that the observation time is much less than the time to crystallization, but in a sense is much longer than the relaxation time of the liquid. So that would be the supercooled liquid, in the supercooled liquid. Now, on the other hand, in the supercooled liquid, you know that any of the time scales of the metastable states is less than, again, the time for relaxation, because the system samples those metastable states. Okay, so this is a conceptual problem, which is that once you're able to escape a metastable state, the very concept of a free energy landscape no longer makes sense. Okay, so this is something which is a tricky part for going from mean field to finite dimensional systems. Of course, it has some interesting aspects because that's what will give you activated dynamics, which is not contained in the mean field, but that makes the problem extremely hard to describe, and basically the the progress so far is still limited on this aspect. Now, maybe I will conclude here, but give you, if you wish, a little, because that might be useful maybe from one of Giulio's lectures, give you a little exercise, if I can find it, about doing an instanton calculation, which maybe some of you know how to do. So what I did, of course, was classical nucleation theory, but you can do it, as I said, by field theoretical methods and instanton calculations. And since these are techniques that are useful in general, you might want to do this. So, okay, you say, let's take the simple stuff first. Okay, so you have a phi-4 theory. Okay, so you have a potential which is like this. So let's say minus tau over 2 phi squared plus g over 4 phi to the 4th. Okay, and you have a, so this is just a potential. Of course, what you do as usual is that because you want to be able to describe fluctuations, so you add a gradient term. Okay, so you have a an effective Hamiltonian, an effective free energy, or an action, which is just, you know, something which adds a gradient term. X here is d-dimensional. Okay, it's just not, and plus via 5x. Now, of course, what you have in the description, the mean field description, is that you have only those two minima, and you can be, and you say that the barrier here, as I said, goes like the volume of the system. But what we know is that it's not true, because you have localized, well, not localized instead of being finite, but you have less than volume dependent excitations that are, of course, domain walls. So basically, what you can do in that case is derive the formulas for having a domain wall, you know, where you would go from phi 0 to minus phi 0. And you know that the free energy of this domain wall will be, so let's say the system is of size L. And the free energy of this domain wall will go as sigma to the L d minus 1. Okay, and then you can calculate sigma as a function of the parameters, and you can show that indeed you can find the domain wall solution as a function of one distance here, and you can show that the excitations goes as the surface now, you know, not as the volume. So it's less than this naive barrier here that would go in the volume. This one goes that the interface is just a domain wall. Okay, so this is a fairly easy calculation. And to do this, what you do is that you find, again, it's still in a sense mean field-like. That is, you're trying always to find maxima or minima of your action. But then you're trying to find some of them with inhomogeneous profiles. Okay, so that's the whole trick. So you maximize this guy, you know, by functional derivation, and you try to find a solution that looks more or less like this, and it's easy, you know, with in that case. Now, if you want to do it slightly harder, then you deform your system. Okay. Then you add a cubic term. So let's say if I put the 0 here, let me put the 0 here, it will be easier. Okay, so now you phi squared. You have a cubic term that makes the metastable state, and then you're asking yourself the same calculation I did before, which is, can I find a droplet, a spherical droplet, you know, size r, that is the maximum, you know, that is a barrier state, that is a maximum of the action. Okay, so you will have, if I draw now since it's a radial symmetry, okay, so we'll have a droplet of size r, and r is just the radial distance, then you will have phi here that will be, something, and go to here the metastable value. So I put the stable value at 0, so it will be roughly the metastable value. Okay, and it will have again a width and a distance r. Okay, and it's easier to do. In that case, it's a pretty tricky calculation. So to do it completely analytically, it's easier to do it what is called in a thin wall approximation when this is much less than 1. Okay, this is called the thin wall approximation, which is true when this guy here is deep down. Okay, so this is again finding all this are called just instanton calculations, which means that you're trying to find localized, well, in that case it's truly localized, or inhomogeneous solutions that are, in that case, still maxima of your effective Hamiltonian or action, but still are much better description of your system than just the homogeneous Landau description. Okay? And this is, in that case, you find the interface and surface tension. In that case, you just find back, actually, the classical nucleation description that I just gave you before. Okay, now, and Giulio will do a fancier calculation in a day or two using those kind of techniques. So if you want to work on this, it will be a preparation. But otherwise, you can do it after his lecture also. I'll be around anyhow to give you help. Okay, do you have questions? I'm done now for this course. If you have additional questions, then please.
Can you say again why the notion of energy landscape didn't work?
Why the notion of
Energy landscape didn't work in a certain time scale, which you mentioned earlier when you did that part. I lost that.
Oh, okay. There are two. Let me just then. There are two notions. Okay, there is that one should not. Okay, there is the energy landscape. One should be, I guess, clear about this. Is that there is there's the energy landscape, which is one thing. Okay, this one is defined even for a liquid. A liquid is you have an energy function of all the n coordinates of your particles. Okay, so the 10 to the 23rd, whatever, and this is just a hypersurface, and this is always defined. Okay, there's no problem. And it's even independent of temperature if you work at constant n, constant volume. So this is always defined. So this is again, and so on in 10 to the 23rd dimensions. So this is again bad representation. This is defined. The problem is that again, you're not sure that the minima are meaningful in a sense that, remember what I said about the dynamics, is that the minima are meaningful if you spend time around the minima. To vibrate, to explore, to do something. Something that describes a bit the separation of timescales that we had. If your minima are such that, of course, again, this is a wrong description because the barriers, remember, are localized, whereas the energy difference are order n, so this is a pretty bad description. But if the minima are just so shallow that the system just goes from one to another just with very little time, then what's the point of looking at the minima? You need to look at something which is on a different scale on which your system will be localized. So this is what you do when you look at a free energy landscape. But again, the free energy landscape is well defined only in mean field. for reasons that I gave. That is, metastable state, if you can escape, then your free energy is convex, and that's the end of it. Okay, so what you like to do is something in between, where you can coarse grain, in some sense, your energy landscape, so that you put all your little guys that are irrelevant in a bigger basin, actually what Frank Stillinger called meta-basins, and then you look at the landscape which is coarse-grained, so it's something which is in between those two guys. But it has to be defined now by a time scale. Okay? That is, you coarse-grain your states, and then you say, okay, I coarse-grain states that are separated by barriers less than this or that. What is nice in mean field is that since all barriers are infinite, then you can count the free energy states and do the whole calculations. Okay? So that's the distinction between the two concepts, and it's a hard problem of glassy systems in finite dimensional context. Okay? If you're interested by mean field or random graphs, then of course mean field is fine. But if you're interested by finite dimensional systems and glasses, then you have to worry about this problem. Okay, more. You're stunned by what I said? Is that the? If not.